The following talk is titled Control System Cyberattack Detection Using Lyapunov-Based Economic Model Predictive Control. It presents work performed by Henrique Oyama and Helen Durand in the Department of Chemical Engineering and Materials Science at Wayne State University. In this talk, we focus on control system cybersecurity issues. Cybersecurity is needed for maintaining expected operation of critical industrial components and infrastructures. Attacks on industrial control systems can seek to impact various concerns, such as profits and safety. Information technology solutions provide one means for addressing cybersecurity concerns for control systems. Other engineering strategies can also be explored. For example, it is important to look at methods for trying to detect attacks when they occur. Potentially also methods for designing systems to be able to withstand attacks. And finally, looking at control designs that can try to aid in preventing cyber attacks from causing problems for a system. Despite advances in these areas to date, additional strategies are needed to enable nonlinear systems under advanced control laws to be made cyber attack resilient. Control theoretic advances may aid in this direction, including in detection of attacks. Effective methods of detecting attacks provide a step toward cyber attack resilient control systems. In this talk, we will seek to develop attack detection mechanisms based specifically on control theory pertaining to an advanced control formulation known as Lyapunov-Based Economic Model Predictive Control, or LEMPC, which is a model predictive controller that explicitly optimizes economic performance and incorporates Lyapunov-based stability constraints. Our motivation for exploring cyber attack detection with respect to this control law is that it has strong theoretical properties even in the presence of sensor noise and plant model mismatch. We will explore two concepts for using this controller to attempt to detect attacks. One in which an output feedback LEMPC is designed with an attack detection strategy based on redundant state estimators, and one in which LEMPCs are randomly updated online to probe for cyber attacks. We consider a class of input affine nonlinear systems with bounded disturbances and bounded inputs. We consider that the origin of this system is stabilizable, in the sense that there exists an explicit stabilizing control law, h of x, that can render the origin of the system in the absence of disturbances asymptotically stable, in the sense that there exists a Lyapunov function v for which the time derivative along the closed-loop state trajectories under the controller h of x is negative, for all x in a neighborhood d of the origin. We define a level set of the Lyapunov function in D as the stability region, omega rho. We also consider that there are m sets of outputs that are continuously available, and we allow for bounded measurement noise. We assume the existence of a deterministic observer for each of the m sets of measurements, which can be utilized to stabilize the closed-loop state within omega rho when used for providing state estimates to the controller h of x, and for which the estimation error can be bounded after a time tbi. Now that we have defined our class of systems, we can use it in defining cyber attacks. Cyber attacks can be understood in a dynamic systems context and can be performed on different elements of a feedback control loop. For example, an attack could break the feedback loop by providing false state measurements to a controller instead of sensor readings. This is the type of attack we will focus on in this talk. False sensor reading cyber attacks prevent true process knowledge from being obtained by the controller. However, it has previously been suggested in the literature that state estimation may help with reconstructing falsified states and detecting attacks. A general formulation for output feedback economic model predictive control is shown here. Economic model predictive control, or EMPC, is an optimization-based controller, so it computes control actions by solving an optimization problem, minimizing the time integral of a general and potentially economics-based stage cost LE, subject to a process dynamic model, state estimate, and input and state constraints. An output feedback EMPC formulation, which our proposed method for cyber attack detection builds on, has been developed with theoretical guarantees in the presence of bounded estimation error and with additional constraints. However, the bounded estimation error assumption could be disrupted by a cyber attack, so that attacks must be detected to prevent closed-loop stability issues. The output feedback EMPC formulation, which our work will build on, is shown here. As noted on the prior slide, This formulation has additional constraints beyond those shown on the prior slide. These additional constraints are Lyapunov-based stability constraints, and there are two sets of such constraints. The first, shown here in red, are the Mode 1 constraints and correspond to allowing the state predictions in the LEMPC to vary throughout omega rho E1 while guaranteeing that the closed-loop state stays in omega rho. The stabilizing controller h of x is used in the constraint design and is a feasible solution in sample and hold at every sampling time. This Mode 1 formulation of LEMPC with state estimation-based feedback can keep the closed-loop state and state estimates in omega rho in the presence of bounded disturbances and measurement noise. The second constraint of LEMPC, or the Mode 2 constraint, is shown on this slide in blue. It is a contractive constraint that ensures that the computed control actions decrease the value of the Lyapunov function over the next sampling period. If applied consistently, this constraint could drive the state to a neighborhood of the steady state. This completes the background on LEMPC with output feedback. Now, we look at how such a control design might be used in cyberattack detection and resilient control. This is the first of the two cyberattack detection concepts to be presented in this work, and is motivated by the fact that the stability results of the prior section rely on the state measurements having been behaving according to the expected noise profile. If a cyberattack on the measurements occurs, it may not satisfy the expected conditions and has potential to impact closed-loop stability. However, the properties assumed for the state estimators suggest that redundant estimators could aid in attack detection. Specifically, given the assumption that the state estimate and actual state eventually come within a bound for each estimator, a maximum difference between the estimates from any two estimators can be derived for the case that no attack occurs. This difference can be checked to see whether it holds at every sampling time to attempt to flag falsified sensor measurements if it does not hold. In this work, we consider that only the state estimate received by the LEMPC can be impacted by an attacker. Then, at every sampling time, we check the difference between the estimates from all of the estimators. If this difference is within the expected bound, an attack is not flagged. If it is outside the bound, an attack is flagged. Even if an attack has occurred that keeps the difference in the estimates of all estimators within the bound, the closed-loop state will be maintained with an omega rho over the next sampling period because essentially the attack is sufficiently small that it is compensated by the design of the LEMPC, as long as the LEMPC is designed to satisfy sufficient conditions such as having a sufficiently small value of rho E1 and of the sampling period. We now move on to presenting a second cyberattack detection concept. This concept again makes use of the stability properties of LEMPC in its development, but here we will consider the case of full state feedback, so that where we used to consider estimates in the LEMPC, we now consider a full state measurement. We also will consider that we can develop a number of Lyapunov functions and Lyapunov-based controllers with stability regions in omega rho 1, where the time derivative of each of these functions is negative under the Lyapunov-based controllers in these stability regions. When we design an LEMPC with respect to one of these additional Lyapunov functions and Lyapunov-based controllers with the Mode 2 constraint, shown in red on the left, consistently active, then the value of the Lyapunov function should decrease between two sampling periods after this LEMPC is activated, as long as the closed-loop state is not yet in a neighborhood of the origin around which the controller is designed. This suggests that attacks may be detected by activating these auxiliary LEMPCs with the contractive constraint over time, and then checking whether the activation of the ith controller results in a decrease of VI over the subsequent sampling period. To summarize, this methodology works as follows. An LEMPC designed using V1 and H1 is used the majority of the time to operate the process in omega rho 1. At random times, to avoid evasion by an attacker. An ith LEMPC formulation, designed using omega rho I, VI, and HI, is activated for a sampling period, but always with the Mode 2 constraint active. When this ith LEMPC is activated, VI should decrease over the subsequent sampling period. If it does not, potentially an attack is occurring. We know that this is not guaranteed to locate cyber attacks. Now, we demonstrate this second concept via a chemical process example. We consider a continuous stirred tank reactor, or CSTR, in which a second-order A to B reaction takes place, with the dynamics noted here. The control objective is to optimize the process economics while maintaining the closed-loop state in omega rho 1. The objective function is based on the production rate of the desired product, and manipulated input constraints are used for physical reasons. We can also write this model in an input affine form with the origin at the steady state by defining deviation variables from the steady state. We then define the Lyapunov-based controller based on that process model to keep the component of the input corresponding to the inlet concentration at its steady state value, while designing the component for the heat rate input according to Sontag's formula. A quadratic Lyapunov function is used with the form shown here. The upper bound rho 1 on V1 in the stability region is 300, with omega rho A1 as a subset of omega rho 1. A prediction horizon of 10 and sampling period of 0.01 hours are also used. To illustrate the second cyberattack detection concept with the nested level sets of the Lyapunov function, we need to define a region omega rho 2 within omega rho 1 that contains the current state. At T0, such a region is found around a new steady state xd, and a new quadratic Lyapunov function V2 is used to define omega rho 2 around this steady state, with rho 2 equals 100 and rho E2 equals 75. This region omega rho 2 is shown in green in the larger region omega rho 1 in the figure noted. When this new stability region is used to define a new LEMPC, starting at T0 with the mode 2 constraint activated at all times, then in the absence of a cyber attack, the closed-loop state can be driven to a neighborhood of this new steady state if that new LEMPC continues to be applied. In addition, we see that V2 decreases over the sampling period following the switch, as reflected in this figure. However, when a cyber attack occurs that provides a false state measurement starting at T0, the same time as the probing starts by activating the LEMPC defined with respect to omega rho 2, then though V2 should decrease in the sampling period following the activation of this new LEMPC, it does not, signifying a potential attack condition. In conclusion, detection mechanisms using LEMPC may take advantage of control theoretic guarantees in detecting cyber attacks on sensor measurements. We looked at two different concepts for this in this talk. One was a cyber attack resilient output feedback LEMPC that combined state estimation, detection, and control. It assumed that multiple state estimators were available for the process and that the one used by the LEMPC could be compromised by a false sensor measurement attack. However, through a strategy that looked at comparisons between different estimates from different estimators, it was determined that the resulting framework allowed for either an attack to be detected or for the closed-loop state to be maintained within a well-characterized region of operation. The second detection mechanism we looked at explored randomized changes to the LEMPC formulation to probe for attacks. This included randomly modifying the control law in a way that should create a specific outcome if no attack is occurring. There is no guarantee, however, that this detects an attack. We would like to very much thank the National Science Foundation and Wayne State University for their financial support. Thank you.